All right, good morning, guys. Yeah, hi, Johnny, Mark. Good. You guys are just in time. All right, so hey, let's check out the announcements. Yeah, for today, just like the usual Wednesdays, there's nothing more to say. Okay. And so that's we can we can just go ahead and check out the topics today. Okay, so there's gonna be two sets of topics today. First part is to continue talking about the IPv4 address. Okay, so the first topic, DHCP, is related to how you get an IP address. You see that for each of our laptops or smartphone to connect to the internet, they need an IP address. So how do the laptops and smartphone get an IP address in the first place, right? Did you try to configure the IP address for your machine? Usually no. Okay, but that is not the only. DHCP is the protocol that allow you to ask for an IP address from the network you join to. Okay, but that is not the only way to get an IP address. There are two ways. Let's check out the first video. Let's talk about how a host gets an IP address. There are two ways, especially in the older time. You have to talk to the system admin first. System admin is going to give you the IP address. And then you manually type up the IP address at the specific place in an operating system. Now, how you do that can change from operating system to operating system. Where you do it exactly could also vary within the operating system from version to version. And some of you might need to reboot the machine as well in order to have the IP address taking effect. So this process here, the manual approach, very tedious, out of fashion. More fashionable today is to run DHCP, the Dynamic Host Configuration Protocol. What it does is to get the host and IP address automatically and configure it automatically. The service is entirely plug and play, so there's no manual effort required. Really nice. And we're using it every day. This DHCP protocol is already part of the protocol stack and part of the operating system, part of all the operating systems these days, including the mobile phone operating system. So formally, let me introduce DHCP. It allows us to acquire IP addresses dynamically. So what happened there is that our side of DHCP is running the client process. The subnet you'll be joining. The server process is running on the subnet, running on one machine on the subnet. So the two sides, client server, will negotiate and reach an agreement. So that agreement is actually a lease on a specific IP address. And that's why my host here gets to use a specific IP address. So with this, we bypass needing to communicate with the system admin, a real person. And the assignment is also automatically done because it's all part of the operating system. But essentially, after the negotiation, we get to use an IP address. But as you see here, it's a lease, meaning the IP address is also temporarily allocated. So that is why it's called the dynamic host configuration process. It only runs for a while. If you leave the subnet, this IP address will be reclaimed by the server. But don't worry, as long as you stay in the subnet, stay connected, stay on, then you get to reuse the IP address. And this is done by exchanging messages again between the client and server. So there are some more messages being exchanged and periodically so that we could renew the initial lease. So that is generally how the DHCP works. You see, this is really, really nice for us living now a very mobile lifestyle. And the process is very simple. This negotiation process is very simple. A very simple four-way message exchange. And an even simpler version is just two-way exchange. So these two first messages, they can be actually bypassed if the user is coming in and out really fast. Typically, the OS on a smartphone implements more this version of DHCP. Let's take a look at the scenario and go through these four messages in a bit more detail. So here it is. We've used this network already earlier to explain, right, what's IP address format and what is the subnet address. So let's assume we set up a DHCP server here connecting to 223.1.2 subnet. And we carrying a laptop, okay, running an operating system with the client process already running. So the arriving client process here, server process here. All right, so that's the scenario. Next, I'm going to show you the exchange of those 4 messages. But pay attention. As you walk in with your laptop just turned on, there's no IP address on your machine. Okay. How do you discover the DHCP server in the first place? Yeah, it is not exactly easy. Okay, so this 4-message exchange is done in a quite delicate way. Pay attention to the destination address of these messages are assigned to. The first message, DHCP discovery. What it does is the client asking, in a broadcast way, yeah, is any of you guys the DHCP server? So if we look into the packet, you should see the source looking like this, a null IP address. And the DHCP client is default on port 68. The server, on the other hand, on port 67. Destination will be going to the DHCP server. But hey, the client doesn't know if there is a DHCP server in the first place, not to mention the exact IP address. So we're sending it to here, the broadcast IP address. A message carrying such an IP address is going to be received by all hosts on the subnet. Therefore, DHCP server being one of the hosts on the subnet will definitely receive the discover message. Why I address here? Yeah, this is the field to store. The IP address potentially will be assigned to the client. Now, the client has no clue, therefore, it's null. Last is the transaction ID. Now, this is actually quite critical. Usually, it looks like a random number. Okay? Different clients will actually send discover messages carrying different transaction ID. Now, these IDs are also to tell the arriving clients apart. So there could be other clients arriving as well. And they could be sending these DHCP discover messages about the same time. Servers sending responses, DHCP offers, okay, about the same time. How does this guy know which offer is for this guy, and how does this other guy knows, right, which offer is for him? So transaction ID, okay, typically different, coming from different clients to enable the clients to tell whether the reply is coming for the host or not. So very important. And to respond to the discover message, the server sends the offer message. Okay, so this is saying, yeah, I'm here. And here's an IP address you could use. And inside the offer message, you see the source being the server's IP address. Destination, again, the broadcast address, because arriving client doesn't have an IP yet, but will still receive a message going to the broadcast IP address because everyone on the subnet will receive such a message. And we see here, the server is offering this IP address to the client. Transaction ID, yep, the same pair. Okay, so this offer is for this discover message. And you see, server here, while offering a specific IP, is also saying, hey, client, you get to use this IP address for 3,600 seconds long. Okay, so it's the duration of the lease. Client then say, yeah, DHCP request, okay, I'm going to take the IP address, and this is the content, asking for this IP address. And it's a new transaction for the song. In return, the server sends back ACK, okay, which is simply saying, okay, you got it. Okay, therefore, you see, you got the IP address for this song. And this, again, corresponds to this, okay, not to be confused with other clients requesting for other IP addresses. So this is the exchange of the 4-way messages, okay, in DHCP service. Now, in the exchange, DHCP server actually say more, okay, not just the IP address, but a whole bunch of other things that are very critical setting up, okay, the subnet on the hosts. So first is who the first hop router is, because the host message is going out onto the subnet. The default next hop is always the first hop router, because the first hop router then, after picking up, then can determine where else to forward it further. Another important information, yeah, DNS servers. This is very critical, right? Because you are requesting www.google.com or www.something, okay, by the name of the server. Okay. In order to know the IP address, you also need to configure on your host the DNS servers. Okay. I know some of you might have some DNS server IPs assigned already, configured already, but if you connect to DHCP server is going to also, okay, add some IP addresses into that part of the operating system. Okay, so the name and the IP addresses of some DNS servers by default. And then the network mask. So this is to tell the host how long is the subnet part of the IP address. So provided the IP address, the DHCP server is also saying that, hey, what is the subnet part? And therefore, okay, the client also know what is the host part. All right, so you see that DHCP offers you a temporary IP address, but in the meantime, it also tells 3 more information so that you can connect to the subnet. All right. So first of all, you need to know the subnet address, right? That's the subnet mask, meaning how long the network part of the IP address is. And then 2 additional information. Who's the first hop router? And that is the router you send all the traffic to pretty much. Okay. And second, DNS server. Okay. Otherwise, you won't be able to find the IP address of the destinations you want to go to. Okay. The last video about DHCP is very interesting. Okay. Pay attention. That might remind you of how DNS is implemented. And you know what? DNS is introduced as an application layer protocol. DHCP, we talk about it in the network layer, but you will see also that DHCP is still an application layer protocol. So here's DHCP and how it's implemented. And to illustrate, you see in this DHCP example, host is right here. Okay, we just joined. And DHCP server is already up, and it happens to be running on the first hop router. So what happened there is, the connecting laptop is going to send a DHCP request message out to the network. So this is the simplified version of DHCP. Sending request and server sending ACK. So the laptop here is asking for its IP address. In addition to that, first hop router, DHCP server, and netmask. So DHCP is actually right here, an application layer protocol. And that DHCP discover or DHCP request message is going to be what? Pass to the UDP and adding the UDP header, push down to the network layer and adding the IP header, and push down to the Ethernet and adding the Ethernet header and trailer. So the DHCP request gets encapsulated into an UDP packet, further into an IP packet, further into an Ethernet frame. So you know DHCP is actually implemented at the application layer. Just like DNS, seemingly a lower level functionality, a general functionality, okay, for everyone on the internet, but implemented at the application layer. Complexity at the edge. And it's using UDP as the underlying transport layer service. Now this frame, okay, carrying destination address being broadcast 255.255 all the way, is going to reach all the hosts on the subnet. So this is the entire subnet. By the way, this is an Ethernet switch. It's a rectangle, not quite a circle, so this is not the router. Okay, so this is actually the link. Okay, so this interface and this interface are connected through this link. So every host on the subnet is going to receive the DHCP discover message. So therefore, the server here is going to pick it up. So this is what going to be extracted, okay, and pass up to the IP layer. This extracted, pass up to the UDP, and this extracted, and eventually reaching the application layer. So the server then can see, this is a request message, therefore send back a reply. So you see here, going all the way, Ethernet gets demuxed to IP, to UDP, and finally, server side of DHCP. Now, the server then will generate the ACK message containing the IP address of the first hop and the IP addresses of the DNS servers, and so on and so forth. So process is very similar, encapsulate to UDP, encapsulate to IP, Ethernet, and destination address being broadcasted. The host here, although not having a specific IP address, is going to pick it up. Okay, so the client now knows the IP address of itself, name and IP address of the DNS server, and the first hop, as well as what? The network mask. So what I'm showing here is the result of sniffing DHCP messages. This is a DHCP request message, and this is a reply of that. Earlier, we actually called it the ACK packet, okay, ACK message. And I can use tools like Wireshark or TCP dump to sniff packets travel the internet. Now, after sniffing, you're going to see the content inside the packet. So what I'm showing here is, this is the request message. So you see boot request. And in the reply or in the ACK message, you see it says boot reply. And you see transaction ID, transaction ID, and they're identical. So this ACK here is for this request. And then you see also specifically the client not having an IP address, but it still have a MAC address. So that MAC address is actually hard-coded into the network interface card that came with your machine. Okay, so that is already existing. And that is something that the DHCP client is going to send to the server. So server can identify you somewhat by the MAC address. And then, this is DHCP request, okay, and this is DHCP ACK. And the client is asking for these, right? So the IP address, okay, so IP address is not clear yet. So requesting, this IP address. Okay, so this is not a sure thing. It's just that the client suggesting, can I get this IP address? And it's also asking for domain name servers, and the subnet mask. Server here, in the response, you will see, okay, hey, client, okay, it's okay to use this IP address. Go ahead. In the meantime, it's returning also the subnet mask, the first hop router, as well as the IP addresses of the DNS servers and the domain name. So all these information, client can then set everything up and then begin to access the internet. Alright, so that was DHCP. Very much like the DNS protocol, right? And why do we implement such an important network layer functionality at the application? Complexity at the edge, remember? So Gladys asked a very interesting question. Okay, so if you recall the first video about DHCP, when we walk into a Wi-Fi subnet, okay, so what our laptop is sending is a message, right, asking for an IP address, and that is destined to 255.255.255.255. It's a broadcast address. So anyone existing on the subnet can reply. So that is actually a potential point of attack. So nowadays, how you get an IP address is a web authentication first, and then DHCP. So those who do international travel more frequently, you might find that when you come to an airport and you want to use the free Wi-Fi in the airport, you need to connect, right? And then usually when you try to connect to the airport Wi-Fi, there's a web page that's going to pop up and asking you to log in and stuff, or providing information before you can do DHCP. And of course, your smartphone or laptop doing DHCP, it's actually just automatically working without you noticing. Okay, so all you are aware of is just typing up your email address so that the airport authorities will provide the DHCP service. Okay, but you see also that one can try to hacking by connecting to the network and try to respond faster, than the web servers set up by the airport. Then they can harvest email addresses or potentially passwords that you use commonly. So when you access these public Wi-Fi networks, public whatever networks, be careful. Connect to your VPN first before you do anything else. All right. But I'm actually not quite sure whether you can connect to VPN without DHCP first. Okay, so hey, Gladys, next time you're traveling, try connecting to VPN first before you try to connect to Wi-Fi and see if it works. So you have the 4G, 5G network, right? Connect to VPN first, and then try if you can connect to Wi-Fi and set things up. Okay, security. 健身 rogue DHCP for some information. Okay. So 健身 is suggesting just Google rogue DHCP. Okay, it is a well-known security threat. Okay, so if you go to Starbucks, go to some coffee shops, okay, you might be looking for free Wi-Fi you can connect to. Just be very careful. okay, using those public space Wi-Fi's. Now, speaking of public space free Wi-Fi, that is exactly quiz 33. Oh, sorry. Quiz 33. Okay. So, have I told you that I like to read? Yeah, I do read a lot. So this is one of the news I find interesting, okay, a few years back. And sorry, international students, the news is in Chinese, okay, but no worries, I've translated, okay, the news here. So the title was more like, you never get connected. So these free Wi-Fi services in Taiwan, don't expect high to them, okay. So translated, the content of the report reads more like this. There are quite a few these free Wi-Fi access points around Taiwan, provided as a friendly gesture to the travelers. Nice. But, everything has a but, okay? But, 40% of the users are not really happy about these free Wi-Fi services, okay? Among these people who are not happy with the service, the highest percent of the complaint is this. They complain that they don't get to connect to these free Wi-Fi at the first place. Now, the second highest complaint is that, so these 60% of the complaint says that they are able to connect, but the speed is low, the signal is weak, and if they just walk a little bit, they lost the signal, lack of AP spots, etc. So, Q1 ask, and focusing on this, the highest percent of complaint is this. They couldn't connect at all. What could be the cause of the trouble? Okay. And given the trouble that you can think of, how would you address so that you can remove that trouble? Okay, so this is quiz 33. Let's now move to the score. Go to channel week 13 and quiz 33. Okay, guys, this is finally again a open-ended problem. Okay, so you're allowed to be creative. Okay, but don't forget about associating with the topics we just talked about recently. All right. And this is also being an open-ended problem. You might want to gather your teammates and have a little bit of discussion. Okay, and for the purpose, you guys are given 8 to 10 minutes of time, okay, to think it through, and think of also solutions to address what the problem might be. And let's start. Okay, I see 2 teams already, and more teams are busy typing up your answers. So let's check out. Elaine representing team 2. Okay, they thought the trouble of not being able to connect is because all the IP addresses, okay, available at that DHCP server runs out. Is that possible? That is very possible, right? If this is at the Taipei station or the Taipei International Airport, people come and go. There's just so many people around. I think these IP addresses are easy out. Okay. So this is I think top 1 cause of not being able to connect. All the IP addresses available on the DHC server are assigned. Okay, someone has taken some. The people around you have taken all the IP addresses. How to address this problem? Okay. Oh, private IP block. Okay. Okay, so this is a notion that we have not yet talked about, okay, which we will talk about two topics down the road, okay, NAT. So one can actually set up NAT such that even though this DHCP server is assigned just one IP address, real IP address, we could use the NAT there doing IP address translation. So within NAT, we could have 2 to the power of 32 IP addresses to assign, okay? As long as they are translated back to the real IP address and forth, okay, back and forth, okay? So this is how one tried to sort of multiply, okay, real IP addresses to IP addresses that is required by all the machines within this NAT subnet. We'll talk about this 2 topics down. Okay, so this solution is a little bit futuristic. Elaine, team 2, I don't know how you guys. I think the reason that you guys came up with the solution is probably Gladi. Okay, yeah. So Gladi obviously know more than the rest of the class. Good for you, Gladi. And team what, Mark? Oh, okay. Hey. Very, very good exercise of your creativity and ration, okay? A very good exercise of how you associate, okay, the quiz problem with things you know. Okay, let's see. Too busy. All IP addresses are occupied. Okay, this is a top reason. Not just network, but also the server. Okay. How about the DHCP server itself is too busy so that it couldn't answer the request? Okay, so maybe there are IP addresses, but the DHCP server somehow is too busy. I think, for example, bad memory sticks in the server itself might create a problem like this. Okay, or weak network interface also. Bad coverage of the Wi-Fi. Yeah, okay, so I think you meant the radio coverage. Okay, so when the signal itself is weak, yeah, you had trouble really sending the IP address request at the first place to the DHCP server. Okay, and you never get connected. So this is a little bit different from the other complaints saying that there's lack of IP address, that there's lack of AP coverage. That is more because they connect, but as they walk around, they lose the connection. Okay. And this is if you are far away from the AP, of course, your request message never get to the server. Server might be okay. There might be plenty of IP addresses. But if you are far away from the AP, that request message might not get to the server correctly. Okay. Hardware quality. Yeah. Power unit. That's right. Low bandwidth, weak throughput. Yeah. I think a hardware defect. Okay, a lot of times, okay, if you see instability in the performance, um, most likely hardware defect. That is also saying that you kind of need to do some performance check to make sure that all the pieces on your computers are okay. I think there are tools, softwares these days that allow you to check how many times your SSD cards has been written on or read from. Okay, and when the time is right, you would really like to duplicate your data to a new SSD and get rid of the old one before the old SSD crash entirely. Okay, that will be a disaster. Okay, Q2. How do you address each of the problems? Kill connection that is not active for a long time. And buying more powerful. Yeah, so get an AP such that it runs on a higher power voltage, therefore the radio range can be wider. Come up with some efficient fair algorithm to okay, so a certain way of allocating IP addresses. Okay, some time limits. You know what? In DHCP protocol, there's a lease time. Okay. Yeah, one can probably come up with a way of assigning the lease time so that it would address the issue that people might be coming going quickly. Because as they come and go quickly, the time they remain in the subnet might be very short, right? So the lease time doesn't need to be long. Okay, but if the users tend to be staying in a room covered by an AP, so for example, lecture room around campus, then maybe the lease time can be longer. Okay, I guess it depends a little bit on the scenario, the situation. All right, good. I see you guys all kind of come up with something on your own. Q, no connection. Too many people trying to connect. Slow connection speed. Okay. A free service for public, it's not easy. Okay. So that was team 9. Let's see. Idris, probably team 3 or 4. Team 3. IP address. And number of AP routers. Build more routers and kill some IP address that are not actively used. Okay. So I guess the DHCP server, in addition to running assigning IP address based on a lease, the DHCP server can probably also garbage collect some of the IP addresses previously assigned but not really actively used in case there are too many requests, okay, that are being buffered and waiting to be served. All right, so let's not go down the channel to check everyone's solution. Polly promised that she will do this one by one. Polly always enjoys grading the open-ended quizzes. All right, but due to time constraint, let's go down and take on the second topic today. Okay, it's still related to IP address. In DHCP, we talk about how a network interface acquire an IP address. Okay. Now the question is, DH server provides the IP address to a computer. How does the DHCP server gets the block of IP addresses to assign in the first place? That's actually done by the admin setting up the DHCP server. And this network admin is constrained also by the address space, the block of IP addresses assigned to him from another authority above. Okay, so this video explains this hierarchy of IP addresses. So that was how a host gets an IP address. We ask the system admin for one or DHCP server for one, which is configured by the system admin. So the bottom line is, how does the system admin get a block of IP addresses so that the system admin can assign to individual hosts? So the next question we're asking is exactly that. Yeah, how a subnet gets the subnet part of the IP address. The answer is quite straightforward. Now, as we ask the system admin for one, system admin asks the higher level system admin for a block of IP addresses. So if we are customers of an ISP, we ask the ISP for the address block. So what I'm showing here is an example. ISP owning a big block of IP addresses. Okay, so by big block, this is how big a block is. Now the prefix of the subnet address of the ISP is only 20 bits, so only up to here. Therefore, that allows us a bigger free IP address space. Now, if there are 8 customers, okay, subscribing from the ISP, organization 0 all the way to 7, ISP can further divide the bigger address space this way, extending the prefix by 3 bits. So that is pushing it further, okay, here. So 3 more bits being included into the subnet ID. Because there are 3 bits, so we could uniquely separate the 8 different organizations. But as a result, we get what? Less free IP space. Each now gets only this much. That is what? 1/8 of the original space. So we are splitting the IP address to 8 equal ways. And it is done very easy by just simply saying this, extending from 20 to 23. Let's say if organization 7 here having 4 departments and each ask for an equal share, then very straightforward, right? Extend from 23 to 25, the prefix lengths. And so we'll be actually doing something like this. Take 2 more bits here, and there are 2 bits, therefore we could identify 4 departments uniquely. And the IP address space is now down to 2 to the power of 7, okay? 1/4 of the second level organization here. So you see, using the prefix there, by sliding it to the right, we actually create also a natural hierarchy in the IP address space and dividing the IP address space. Just like how human beings divide and organize bigger society to smaller society and even smaller society. So this type of addressing, the IP addressing, is also called the hierarchical addressing. There's actually one more benefit of it, not just that dividing the address space is made very easy, but also this. We could do very efficient route advertisements. Now, routing is one of the major functionality in the network layer. We have not yet talked about it, so in order to explain how efficient this is, let me just give you a slight overview of routing. Alright, so before I give the overview of routing, now you see, right? So doing longest prefix match makes sense because the computers on the same subnet will all be assigned the same prefix, right? And the neighboring subnets belonging to the same organization will belong to the same prefix, except that that prefix at the higher level is a little bit shorter. Okay, so hierarchical routing, hierarchical address architecture. Okay. Now the next video is Polly's nutshell explanation of internet routing. The goal of routing is to form these forwarding tables, if you recall, right? Destination IP and outgoing interface. Now, the way these entries are formed is this. If this is a destination, if somebody else on the internet wants to send data to this guy will need to announce its IP address, okay, in an advertisement and travel through the network like this to outside. Okay? That is how the router here discovered, oh, okay, I see a destination potentially this way. So that IP here, and the outgoing interface is this guy here. Now for a guy, okay, who's connected to the internet this way, that advertisement will go down, this other interface. So this other guy here, IP prime, the output interface will be linked here. So that is the general idea of routing. But then you see, for each machine here having an IP address, in order to allow other people sending packets to it, they would each need to send an advertisement announcing its IP address. Okay? And there are these many different IP addresses possible, so potentially worst case, right? Lots of advertisements each of these organizations need to send and travel on these links. And you know what? The most scary thing is this. All these need to go out to the internet, so the ISP needs to send these many advertisements. And that is just not going to scale. Okay? That will be a lot of bandwidth consumption just to send the advertisements. The solution is actually related to the forwarding mechanism in the router. If you recall, instead of listing individual destination IP here, rather we do this individual prefix, okay, and then outgoing interface. So when a packet arrives, the destination IP address matching the prefix, then we send it out on the outgoing interface. You know what? Isn't this a prefix? Isn't this a prefix? So what we're doing, in fact, in the internet is not to send individual IP address in the advertisement. We send an individual prefix in the advertisement. So what's happening there is a prefix in the advertisement gets here. Router here, receiving it, pass it down further. Router here, receiving it, pass it down further, but also add the entry prefix here. And because it's coming this way, so this OIF is going to point to this interface. So when a packet arrives here, matching the prefix, go on this interface, and coming here, this router is going to forward it similarly down this way, and then coming into the organization 0. So by announcing or advertising the prefix, okay, we also draw the data into the organization, and the data is actually destined for one of the hosts in the subnet anyway. So the router is inside the subnet there. We just we'll be doing further routing there to get to the final destination. Nice. So you see, instead, organization 0, 1, 2, all the way to 7 will be sending one advertisements only instead of these many advertisements. What's even nicer is this, the ISP. Yeah, ISP doesn't need to send 8 individual advertisements out, just send one. Because it's very easy to aggregate all these, right? Because this is the coarser granularity covering, right? Superset of all these subnets prefix. So there's just one advertisement out this way. One on the link, one on this link, one on this link. Advertisements, the distribution of it, very, very efficient. And so here, the entry is simply 200 something something 6.0, and it goes on this interface. Data matching this will all fit and then go on here. This router here then will split the packet 8 ways, and by checking the destination address of the packet to these 8 different prefixes and see which prefix match better. So that is the idea, and why we say more bandwidth here. This is the third benefit of doing the prefix matching, in addition to what? Making the forwarding table smaller and the lookup process faster. Alright, so I hope that from that video you see longest prefix matching works magically, okay? Because of how we assign the IP address in bigger organization and divide that into the lower level organizations. Now, the final video about hierarchical routing is this. You can even move one of these sub-organizations to another ISP and it will still work. So the slide here is actually introducing a very interesting scenario. Okay. Organization 1 originally here is moved down here to a different ISP. So that prefix advertisement will travel down this way, and ISPRS will try to aggregate it with the original IP address block. Well, ISPRS will find that unfortunately the two of them are not aggregatable. In this case, 2 separate advertisements will go on out into the internet. The forwarding table here will contain 2 entries. One is starting with 199, and one starts 200 dot something 18.0 and 23 bits. This one is 16 bits. And of course, this entry here, okay, will arrive also at the router here at the internet, on the internet. And therefore you have 200 dot something, 16, and 20 here. So this entry is going to take the packet out this interface. These 2 entries is going to take packet out here. So if there is a packet coming in that is supposed to go to organization 0, it's going to match the first entry, isn't it? Okay. It's not going to match the entry number 3 because, hey, this address space and this address space, they are actually disjoint. Okay? So not going to match this guy here. So packet going for destination organization 0 is going to go down and travel and down to organization 0. So setting up the forwarding table this way, not a problem. Similarly for organization 2 and 3 and all the way to 7. Okay? As long as the destination IP address is matching this, it's going to come down this way. Yeah, I know you're thinking, hey, what if the packet is going for organization 1? You're right, it's going to match the first entry. Ooh, a bit worrisome, yes. But if you look down the table, right, hey, it's going to also match entry number 3. Now, if we call back in section 4.2, what did we say? We're actually not just doing prefix matching, we are doing what? Longest prefix match. So which one is the longer prefix? 20 versus 23. So packet carrying destination for organization 1's machine is going to come down this way here and eventually reaching organization 1. So we're okay, right? So the overhead of sending the advertisements is still very low. Now slightly higher here if it's not exactly aggregatable, but forwarding is going to be fine. And we allow what? Organizations moving from one ISP to another ISP without changing the physical IP addresses. Okay? Therefore, all these servers are running here. They can stay using the same IP address without needing to change the name to IP address mapping. Now, we get the block of IP addresses from our ISP, but next question to ask. How does the ISP get its own block of IP addresses? So it's like saying, hey, the system admin asks the higher level system admin, but higher level system admin asks the even higher level system admin, right? And this goes on. Who's the highest level system admin? Where's the end? Yeah, this organization is the end. So ICANN here is the highest level system admin. This is a non-profit organization overlooking, okay, the allocation of the IP addresses, the allocations of the domain names, and managing also the domain name servers. So very important organization. We normally don't know. Okay, only the people who knows about the internet knows a little bit about ICANN. All right, so that's hierarchical routing. The second half of today is going to be addressing the IPv4 address shortage problem. So the IPv4 address space is 2 to the power of 32, but we're really running out of the IP addresses. So NAT and IPv6 both are here to address those issues. Okay, so that's before we talk about it, let's take a break first. It's now 11:12. Let's resume the lecture at 11:22. Okay, break. All right, welcome back. Now let's start talking about NAT. Okay, one of the solutions to address the IP address shortage problem. NAT, the Network Address Translation Service. This is one of the most used protocols on the internet these days. It's here to address a very serious problem. We're running out of IP address space. Yeah, 2 to the power of 32, it sounds like a high number, but we do have a lot more hosts, a lot more router with network interfaces requiring these IP addresses. Therefore, IP addresses is a scarce resource on the internet. To get one, you pay quite a bit of money. This is also why, okay, if this is home network here behind the local network, your deal with the ISP is often this. You pay a specific amount of money monthly. You get a certain downlink bandwidth, certain uplink bandwidth, and a certain number of IP addresses. Usually you get one static IP address or 4 dynamic ones. Okay? If you pay more, maybe 8 dynamic ones. But essentially, the more IP addresses you need being allocated from the ISP, the more money you pay. So it's not like every family can afford paying that much. So to try to save money, this is what we often do at home. Okay? We just, subscribe for one IP address. And then we create a home network, okay, using some fake IP addresses that we make up, and subnet address that we make up. So instead of asking the ISP, okay, asking the system admin for a block of IP addresses, we can afford it. We use fake, block of IP addresses. So we call this local network or home network. Each of the interface is assigned an IP address on the fake subnet. Okay, so these are then fake IP addresses. Now, as long as we are sending data within ourselves, should be fine. But if we want to send data out, wow, we need to be careful. And that's when we need a NAT server here at the home gateway. So NAT is sitting right here. So all packets that's leaving the local network needs to be using the real IP address, the IP address assigned by the ISP. Otherwise, it's going to be dropped, at the ISP. So now if this guy has a connection to go out, and this guy has a connection to go out, and this guy has a connection to go out, each of these connections to not collide to each other will be assigned a new port number as well here, a different source port number. Source IP address changed to the global IP, the real IP, and the port number changed to a different number so that they don't collide to each other. So that is the general idea of NAT. We'll describe the detailed mechanism slightly later. What's nice about NAT is this. We don't need to ask the ISP for a block of IP addresses, which is very expensive. One is enough, save us lots of money. There are 3 more benefits, in fact, using NAT. What is this? If we want to change the IP address in the local network, we just change it. It's not like, we're changing the IP addresses of the gateway there, which is a global ISP, which is assigned by the ISP. Then we need to inform the ISP we're changing it to somewhere else. Otherwise, traffic is not going to flow through. Okay? But if we're just changing the local machine, then there's no need of informing the ISP. Nice, convenient, so save us time. Third benefit, well, if the ISP is not providing good enough service, we can actually switch to different ISP. And the IP addresses we have on the local machines, we don't have to reconfigure them. We just stay using the same fake subnet address, fake IP addresses. The last benefit is slightly unexpected to many of you. Those devices inside the local network, those 10.0.0.1, 10.0.0.2, those IP addresses are fake ones. Packets originated from outside, from the internet, carrying destination 10.0.0.1 is not going to flow through the internet and reaching the gateway and therefore coming back to the host. Because the IP address of the gateway is what? 138 something. That's the real IP address. That is also what people call the global IP address. And that fake address there is the virtual address, the subnet address. So subnet or virtual address or fake IP addresses are not addressable. By not addressable is what I meant is packets coming from originated from outside just have no way of reaching. So they are therefore not visible from the internet, not visible from hackers in the internet. So it's a security plus, unexpectedly. Yeah, but that security plus, if you think about it, if you want to set up a server inside the NAT, it's not going to be reachable by any of your customers. Okay, so setting up a server within a NAT is always an issue. Okay, so you will need to set up something on the NAT box ahead of the time before your customers begin accessing, okay, your server. All right, so second video here is to illustrate exactly how NAT, the mechanism, works. NAT's mechanism is quite straightforward. Only 3 steps, 1, 2, and 3. Step number 1, you heard about it a bit already. So this is to handle when packet is going out from the local NAT to the world. We'll have to replace the fake IP address with the real one. We'll also replace the source port number with a new port number. Okay, so the source IP address, the source port number, these 2 fields are replaced with these 2 values. And this pair, so 1, 2, 3, 4, okay, are also tracked, okay, being remembered in NAT's translation table. So the source IP and the source port number, as well as the translated source IP, source port number, will be maintained as a pair in the translation table. So when the remote host receiving this packet and sends back a response, in the destination IP address, it's going to be the real IP address, and it's going to be the new port number. So that packet coming into the local NAT, the NAT box there is going to look up the table and find the pair, right? So it's matching this IP address and matching this new port number, and therefore translate the IP address back to the corresponding port IP, source IP address, and translate the port number to the corresponding original source port number. And therefore, you see the destination fields is going to be replaced by the original IP and the original port number. And that packet then will travel the local network and reaching the destination. Let's use some animation to illustrate. It will be easier to understand. So the local NAT here, using a fake subnet address. So this machine here, 10.0.0.1, is sending a packet to a web server, okay, outside of the local network, okay, inside the internet. The packet is going to look like this. Source IP being the fake IP. Source port number being the port the web browser is sitting on. Destination IP, the server's IP. Port number, the web server's port number. So that packet is going to reach the NAT box in the middle, and this is going to be replaced. This is going to be replaced. So 10.0.0.1 is going to be replaced by the real IP. And the 3345 port number is going to be replaced by a new port number generated by the NAT box here. Step 2, the NAT router there is going to add an entry into the translation table so that we know this old IP, this old port number is now being changed to this new IP and this new port number. When this packet reaches the web server sends back a response. Destination address will be the source of the request. Okay. So destination port, the source port number of the request. Now this packet will come back to the NAT box in the middle, and one more translation is going to be done. So this time, the process exactly is this. Let's look at the destination port number, and then go to the table. Look up the entry in the table such that the port number in the WAN part matches the destination port number. Now, destination IP address is definitely going to match the WAN side of IP address, because the WAN side IP address is going to be just 138.76.29.7. So this unique new port number is the key. So destination port number, you look up this value in the translation table. Identify the entry, and then replace the destination IP address with the LAN side address. Okay, port number also with the LAN side port number. And that's why we see destination IP address, now the fake IP. Port number, now the original browser's port number. That's how NAT works. Alright, so it's actually quite straightforward, right? So you set up this NAT translation table. Alright, and the last video, right? So the first video, in the first video we talk about several advantages. Okay, can you come up with disadvantages of using NAT? I guess we just talked about the security plus using NAT is also a disadvantage in case you want to set up server inside a NAT subnet, isn't it? So let's check out the full list of disadvantages of using NAT. Last are the drawbacks of NAT. Point number one, poor number, pretty short, 16 bits only. That is also saying we could have only up to 60,000 simultaneous connections. If the local network there is for home use, this is plenty. But if the local network there is for enterprise use, if a company is there trying to save money and subscribing to only one real IP address, having lots of employees, lots of machines inside, chances high the packets going for one flow might be mistaken, okay, with the other flows. Point number two, NAT is controversial. In the previous slides, you might see the authors of the textbook referring to these NAT devices as NAT routers. But routers are what? These devices in the core of the internet. Now, routers implement only 3 layers of protocol: physical, link layer, and network layer. So routers are also called the layer 3 protocols. Now, layer 3 protocol is supposedly only accessing layer 3 packet header. Layer 2 protocol accessing layer 2 packet header. NAT, if you think about the mechanism again, it's what? Replacing the IP address fields in the packet header. It's also replacing port number, okay, the port number fields in the packet header. IP address, that is a field in the, I know, layer 3 packet header. We learned about the IP packet format already. But port number, if you recall, in chapter 3, the transport layer, port numbers are there to differentiate different processes running on the host. It's actually a layer 4 notion. It's in the transport layer header, in the layer 4 header. So NAT as a router should not be doing that. So those who are against NAT boxes to address the network shortage, IP address shortage problem, okay, argue that we should probably, improve IPv4 such that we have more bits for the IP address field. So IPv6 is the next generation. It's using 128 bits for the IP address, much longer. We'll talk about this later. Point number 3, NAT box. Hosts sitting behind NAT box cannot be reached from a machine from outside. So that was actually presented as a benefit, a security benefit earlier, right? Hackers cannot be sending packets to 10.0.0.1 because that packet is just not going to go anywhere. Okay, not even reaching the NAT box in the middle, the IP address being 138 something something. Right? Only packets with the destination address 138 something something will be able to reach NAT box. Okay? And NAT box there, it will also not know, right, what port number, what local IP address to convert back to reach 10.0.0.1. So, it's actually hard to reach local hosts from outside. So if packets are originated from outside, that's not going to work. Packets originated from inside, however, works. Now we know, right? So from 10.0.0.1, the box tracks the local IP address. Okay, keep it in a table. That packet gets translated using global IP, using real IP, goes out. Packet will come back to the router and the NAT box. Look up the table and then translate back. So originated from inside, no problem. But data originated from outside, big problem. And this is a serious problem for these designers, P2P protocol designers. In P2P protocol, a lot of time we will try to establish connections between one user's host to another user's host. You and me being hosts, we are, chances high, sitting behind the NAT box, sitting behind the NAT router. So we'll have trouble calling directly to each other, setting connection directly to each other. If you recall in Skype's protocol design, making a call, the designer of Skype actually take extra step. Okay? Bob and Alice will need to call a relay peer, and the relay peer will exchange packets for each other. Okay, for these two peers, for Alice and Bob. So, application layer designer now need to worry, okay, in case layer 3 or layer 4 protocol is going to break. Okay, unexpected might happen. So, one layer's protocol designer needs to worry about another layer's how it's designed, how it works. That's breaking the end-to-end argument. So by this here, okay, what I'm saying is this: the reference protocol stack there. Application, transport, network layer. So we say nice about building the network protocols and separate them by layers so that it's modular. Designer in one layer does not need to care about what's inside another layer. Exactly the same thing we are arguing here. Application layer protocol needs to worry about another layer's protocol, how it works. So that breaks the modularity there we have in the original reference stack. And that is what end-to-end argument is referring to. All right, so disadvantages of using NAT. Now, quiz 34. Okay, I ask two simple questions. Okay, Q1, which one would you prefer? Okay, paying more to get multiple IP addresses for your multiple devices, or using NAT so that you pay for one IP address, but you could set up many machines, within NAT. Pick one of the two and justify why. Question number 2. Would you prefer using NAT or IPv6? So IPv6 we have not yet talked about, but in a nutshell, instead of using 32 bits address space, it's using 4 times longer, 120 bits as the address space. So the internet can accommodate a lot more machines with real IP addresses. And we don't need to do fake IP addresses as opposed that we're doing in NAT. So NAT versus IPv6, which one would you prefer and why? So this one is entirely subjective. So whatever you like, just justify why you like it one way or another. So you have only 4 minutes. Let's start counting. Yeah, okay, I see Mark has already decided what he likes or dislike. For Q1, I think it's asking you to choose between buying more IP address versus using NAT. And Mark here is that for private home, using NAT is sufficient. But if you're running a company, then purchasing for access to multiple real IP addresses might be better. So running a business, very oftentimes you set up your DNS server, set up your web server or mail server. It's probably better to use separate IP addresses for each of them. And the reason that you prefer using NAT at home is because money. Yeah. To get an IP address for home access, a fixed IP address for home access, it's expensive. Q2. You're asked to choose between NAT versus IPv6. Okay, so team 1, Mark, you prefer NAT because it's safer. Yeah, so the hackers out there cannot scan you by your IP address. Okay, interesting choice. And oh yeah, team 7. Okay, team 7 also prefer using NAT because it's cheaper. I see. And it's more secure. Okay. But if you are asked to choose between IPv6 and NAT, you prefer IPv6. Having more IP addresses in IPv6, supposedly, right, the cost of getting an IP address is lower. Yeah, we all know that when the resource is scarce, the price rises. So 128 bits, ooh, that's a lot. That's a lot. So this makes sense. Okay. Okay, I see that some of the teams are busy typing, but I think very straightforward, right? So if you are asked to choose between paying more or paying less, then yeah, paying less is preferred. Okay. But if you don't need to pay all that much to get multiple IP addresses, then you prefer the better way, getting the real IP addresses, because it provides a lot more accessibility. Okay, in case you want to set up servers. Okay. Nowadays, people set up servers at home for storage access. Think about you're paying maybe Dropbox, maybe Google for storage. If you can set up a storage at home, network storage at home, then you don't have to pay those. Okay. But that is, comparing the cost of paying Dropbox, Google versus the cost of paying for an IP address. I think paying for an IP address is usually a little bit cheaper. Okay, and it really depends on how much space you need for the network storage. Okay, if the demand is high, then probably pay for IP address. Okay. So I think I get the idea. Everything is budget conscious. Okay, so it really depends on how much money you have in your pocket. Yeah, I see more teams saying NAT and NAT. So team A here, NAT and IPv6. Okay. So it seems for first question for Q1, NAT is kind of unanimous. 6, it's easier to implement. Okay. IPv6 might be expensive. So we don't know. IPv6 at the beginning might be expensive. I think you are right, Loretta. All right, because you actually need some extra mechanism there to ensure IPv6 address will work. So the ISPs might actually, put the cost of doing that on the price of an IPv6 address. Okay. Good. I see that you guys are now, telling more. So NAT or NAT IPv6. Okay. Very good. And you know what? It's time to move on to, therefore, the next topic, IPv6. Okay. Let me give a very brief introduction of IPv6. Last topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial netboxes. And that is why we actually upgrade from version 4 to version 6. The approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are two secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really fast. If we could reduce the forwarding time, processing time, we made the transmission process as efficient as possible. Okay. So you see in IPv6, the header is also changed, okay, to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, okay, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Okay. Therefore, okay, we could establish a more flexible levels of quality of service for these different flows. Okay. You see also header fields there to support labeling of flows, setting priority of the flows. All right, so very brief introduction. Essentially, the IP address space goes to 2 to the power of 128 bits. Okay. Now, the next video is a little bit long, 7.5 minutes, because we need to talk about the packet format of IPv6. The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now, recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Okay. Now you probably recall, right? When we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes. Together 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Poly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? 46, in fact, has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space. So unavoidably, we have very long IP address and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing them away, removing these fields away from the header. Okay. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall, in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row. ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay? And this is done by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see version 4 header, although longer, it looks really clean and compact. Okay. First, the source address. Second, destination address. And the rest is only just 6 more. 1, 2, 3, 4, 5, 6. First, here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths.
Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just the TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field, we also have this in version 4. So the only difference is that this value will always be 6 in version 6. Priority and flow label, these two are new. So flow label here is to allowing us to group a specific set of packets together. Okay, so coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, okay, and packets for yet another flow. So we could separate these packets traveling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, okay, not just the fragmentation fields. The header checksum in IPv4 header, that is removed because to calculate checksum takes time. To check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. And take the risk of some bits in the header being flipped. We might have some, might run into some errors, but chance is very low. Okay. We way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload, so that when we grab the payload and give it to the handler is going to look at the first few lines in the payload, and those will contain the options. Okay. There's one more thing. ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer. Right? In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. Okay. So we also extend the version 4 ICMP to version 6. Okay. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Okay. Allow me to elaborate. Now we don't have fragmentation and reassembly, but the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller, but we cannot fragment this datagram anymore? What should the router do? What can the router do? Okay, so the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. Okay, so there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. Okay, it's a can of worms. So this is IPv6 packet format.
All right, so generally you see that the header looks a lot cleaner than version 4, but the size is not strictly shorter. It's in fact longer because of what? The IP address itself is 128 bits long. Okay. Now, next, IPv6. You see that introducing IPv6 addresses in the v4 world, it's actually not that easy. There's no way we replace the IP address of all the devices on the internet in one day. So it needs to be introduced gradually. So how do we coexist v4, v6 devices? Okay, that technique is called tunneling.
So this topic is a little bit special. Okay, we will be talking about how we move from a IPv4 internet to a IPv6 internet. You see, there's no way we turn down all the routers in the world and upgrade to version 6 simultaneously and turn them back on and hope that they will just work. No way. It's really, really risky. And hey, we are all living in different time zones. What do you mean by having a flat day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah, some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. How do we allow the mix of IPv4 router to IPv6 routers? And the technique, okay, let me tell you ahead of time, is called tunneling. Okay, establishing tunnels, okay, between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Okay. Once it hits this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. Okay. So this router will also be doing this. Okay. Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. All right. So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc. etc. Now, IPv4 packet here, coming from the border of IPv4 and IPv6 connection, is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space, and eventually reaching the other end, okay, the other border between IPv6 and IPv4, and that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet, and then forward it further on onto the native IPv6 space here. Right? This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4. I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. I suppose we have data we want to send from A to F. Okay? Both of them, version 6, they should be able to send data to each other all right. Now the problem is this. Yeah, an IPv6 packet here will travel through the version 6 space. But as soon as it hits the version 4 space, yeah, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. So what's being done, okay, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends, okay, exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Once that is done, then let's consider, okay, A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. Destination address is going to be the other end of the tunnel. Okay, the other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E. Then the IPv4 network is capable of forwarding this packet over, okay, at least to E. So E is going to receive the packet next, and being the border router, and being the other end of the tunnel, E is just going to extract the blue packet out of the red one and forward it down to the rest of the IPv6 space. And this is when F here receive the packet that is supposed to go for F.
All right, so that's how we get the IPv6 packets to travel through the IPv4 network in the middle. All right. Last video today, let's talk about adoption. So through that kind of tunneling, we gradually introduce machines that are running IPv6. So how many of these machines are IPv6 on the internet? Okay, that is...
Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Ouch, pretty low. NIST is a government body there tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 30%, 33% of the US government internet is IPv6. Okay. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Okay. Ouch. But why, right? If you think at the application layer, we have new applications rising. Okay, IG, Facebook, Netflix, other video streamings, okay, Zoom, YouTube. Okay, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, network layer changes, it seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app?
Why? Why is it so hard? Okay. By the way, yeah, on the slide, Polly said that at some point, Google released a number, 8%. That is the adoption rate Google sees. But today, okay, to be precise, March 2023, okay, that's 2 months ago, the adoption rate from Google is 39 to 43%, depending on whether this is weekend or weekday. And surprisingly, oh no, not surprisingly, okay, during the weekdays, we see more IPv6. So I guess that the household users, okay, are still IPv4, but the corporates, okay, so weekdays means people working, okay, the percentage of using IPv6 is higher. Okay. Yeah, so the adoption rate is definitely increasing. But 2 decades, and time is still counting. We are still not yet entirely IPv6. So if the protocol IPv6 has existed 2 decades ago, why is it so hard? Okay, maybe you can try to address quiz 35 and then you will understand why. Okay, and you will definitely understand why Polly keeps saying that, hey, DNS, DHCP, seemingly network layer functionality, but implemented as a application layer protocol is for pushing the complexity to the edges. Okay, because core, okay, is just so hard to change. Okay, so quiz 35 here is about making changes. Okay, so Polly would like to dig up the changes you've thought about you've thought about making. Okay, and by the way, this is a take home quiz. Okay, there's no need to complete the quiz now in the class. Q1 asks, have you ever thought about making changes in your life? Okay. If yes, okay, did you end up making the change? Okay. If you managed to make the change, tell us, is it easy or not? Okay, and why not? All right. Okay, so that's all for today. So let me see if the quiz is on the score. Okay, so the quiz is on the score. Okay, feel free to stay a little bit longer to finish the quiz if you already thought about this. Okay, if not, it's a take-home exam. Just finish the quiz by Saturday, 6 p.m. Okay, with that said, I will see you again next Tuesday. We have not yet completed chapter 4 because all these things we talked about, IPv4, IPv6, these are still the traditional forwarding. We have not yet talked about the modern day forwarding, the generalized forwarding. We match not only the destination address, we could be matching generally both destination address as well as the sending address, sometimes as well as the port numbers. Okay, so I look forward to seeing you again next Tuesday. So that's all. I say goodbye now. Okay, bye.